because here you have one of the cast stages, and when you order reinforcement, you just select it there.
At Randselva, we did a span that was 10 times larger than anything we had done before. And the contractor had never built anything without drawings before. It was a steep learning curve, but I think the end result speaks for itself and has been a proof of concept that it's definitely possible. Then you got to do the last bit by manually.
When building a bridge over a river and masses that are unstable, you cannot use scaffolding. So it was decided to use a free cantilever method over axis 2 over here and axis 3. There are cantilever parts. So you first build a pierce in the middle and then you start working your way out from that axis until you meet the other side.
My name is Eirik. I'm a civil engineer with a master in concrete. I work for the Norwegian National Public Road Administration. On this bridge here, I was control engineer. My work day to day was to make sure that the contractor was building the bridge like it was designed on the models, both inside on my computer and outside here on my tablet.
And for the communication net site, we have used Trimble Connect because it's very easy for the workers to handle Trimble Connect, to show some views of the model, to separate the parts that are being assembled on site. It's very, very useful and very easy and user-friendly.
On complex structures, you have a lot of objects that potentially collide. In a bridge, you might have reinforcement, post-tensioning cables, cast-in objects. But with new software like Trimble Connect and Tekla, you're able to plan past these clashes and detect them in a computer instead of at site, and you solve them. At site, you'll get a clash-free design, saving hours when on site.
For every column, we need 2 extra of these ones, the green.
The contractor used it to enrich our IFC models, and they would enrich these models with information on what kind of rebars had been ordered, logging time consumption per cast unit, cost per cast unit, CO2 emissions, and so on. You want a person at site to be able to sort away 99.5% of the information and only focus on what's important to them on that day. Tekla has that ability. So that combination of good software and a good BIM model makes for a good product that's easy to read and easy to find the information that you're after.
With just drawings, there was always something that was in the way or something that had to be fixed on the site. We just didn't have to even think about when it came to this bridge. They had already picked it up in the design phase of the project.
A point cloud can tell you exactly what's going on at site, even though you're halfway around the world sitting in another office. And an updated model can be sent to a client in seconds. Everyone is up to date on what's going on at site and what the new design is. The BIM model that is on the server, that's your single source of truth. That's where you anchor the post-tensioning cables, and here you have a lot of compression forces, and you have about 250 of these cables going through the bridge. On a free cantilever design, you need quite heavy scaffolding systems for your casting, and those need to be held in place by making holes in your existing concrete, and those holes have to be placed very accurately. And we have about 1,000 holes like that on Randselva. They need to be positioned with millimeter precision. None of those holes were incorrectly placed, and that's nearly unheard of in our industry. In a bridge complex as Randselva Bridge, you have a lot of third-party products like joints and bearings, and normally you would get information on that product by 2D drawings. But on this project, we were able to get those third-party products as 3D BIM objects. So for example, the joint that we used, normally you would have people from the company coming and supervising how to install it. They would spend maybe a week at site trying to fix and help installing them. But since we had a 3D model that we could build around, I think they spent about 2 hours at site just signing off the papers, and that was it. The integration was so seamless.
To explain to you guys, now the abutment, that doesn't move at all, but the bridge moves with heat, and it moves quite a lot with heat, so it's like maybe that much. So that's why you have these bearings. The superstructure here can slide relatively to the abutment, and they glide on these bearings.
I have to drive over the bridge every day to work, and instead of having to drive the small country roads, it's not often we build this big bridges on this part of the country, so it's very fun to have been a part of it and also been a part of the next step forward in technology.
And we are very proud and very happy to have participated on this first challenge. We believe that this will be the future for not only for bridge design but for other disciplines as well.
The projects we have done have been finished on time, been built on budget. I think clients trust us. They trust methodology that we can deliver. Also asking the workers at site, see that they don't want to go back to drawings. They understand their scope of work a lot better. They can collect more data to the model, enrich it with important information. I've been quite surprised how positive people have been when they work with our models.